My name is Nur Azra binti Jamrudi, and my matrix number is CM230417. Welcome to an example of an application of first-order differential equation involving electrical circuit. In this video, I will model an RL circuit using a first-order differential equation and solve an RL circuit problem. The differential equation L times dIdt plus Ri equals to Et can be used to model the amount of current It in amperes in a circuit containing a resistance R in ohm, inductance L in Henry, and electromotive force Et in volts. Another way to say this is the sum of the voltage drop across the inductor L times the IDT and the voltage drop across the resistor R times I is equal to Et, while L is inductance and R is resistance, where both L and R are constant. And the current I of T is often called the response of the system. So this is the diagram of a basic circuit in RL circuit. So the question is, two 9-volt batteries are connected to a series in which the inductance is 1/4 Henry and the resistance is 8 ohms. Determine the current IT if the initial current is 0. So from this problem, we need to recognize L equals to 1/4, R equals to 8, and Et equals to 9 multiplied by 2 because of two 9 volts of batteries, so equals to 18. So 1/4 dIdt plus 8I equals to 18. Now this is a linear first order of differential equation. And let's go ahead and put this in a standard form. So we will multiply all with 4. Plus 32I equals to 72. Now, because of this is a linear first ODE, we are going to solve this using an integration factor. E, the power of integration of 32 dt. So, E, the power of 32t times dIdt plus E, the power of 32t times 32I, and this is must equal to E 32t times 72. Remember, so d over dt, E to the power of 32t times I is equal to 72 E the power of 32t. And now we can solve this for I by integrating both sides of the equation with respect to the t. Integrating of d over dt, E to the power of 32t times I dt is equal to integrating of 72e the power of 32t dt. So now we can integrate the left side with the respect to t and the right side with the respect to t. Power of 32t times I is equal to 72 over 32 e to the power of 32t plus c. But on the right side, we have to perform u substitution. So u is equal to 32t and du over 32 is 32 over 32 dt. So we cancel the 32. So we get du over 32 is dt. After that, we solve this for I and divide both sides with e to the power of 32t. So 9/4 plus c is equal to 0. C is equal to negative 9/4. 9/4 minus 9/4 e to the power of negative 32t. So IT is equal to 9/4 minus 9/4 e to the power of 32 to the power of negative 32t. So this is the function that we're looking for that will tell us the current at any time t. Of first-order differential equation in electrical circuit provide essential tools for analyzing and predicting the behavior of circuit elements over time. By modeling voltage and current relationship, this equation facilitates the design, optimization, and troubleshooting of complex electrical systems, ensuring efficient and reliable operation in various practical applications. And I think that's all from me. Thank you.
Hi, Assalamualaikum. My name is Putri Nur Alam binti Azhar and my metric number is EN230088. Now I will present about the application of Laplace transform in process control, specifically to find transfer function. The objective of my research is to analyze the variable which, when altered, will produce desired manipulation in the result and to solve the differential equation occurred in this engineering field. Now we will go through the equation. The tank shown in figure 1 is initially empty, which mean time equal to 0. A constant rate of flow Q initial is added for time more than 0. The rate at which flow leave the tank is Q0 equal to CH. The cross-sectional area of the tank is A. Determine the differential equation for the head H. Identify the time constant and find the transfer function of system. For the solution as given in the question earlier, Q0 equal to CH, then from the mass formula, which is volume multiplied by density, we will change it into a differential equation. Then we will get d over dt, AH multiplied by E equal to EA multiplied by DH over dt. Then to get the mass flow rate into tank, mass in flow rate minus mass out flow rate, then we will get EA dH over dt equal to EQ initial minus EQ naught. Then the E will be deleted and the equation will be A dH over dt equal to Q initial minus Q naught. Then A dH over dt equal to Qi minus CH, because Q naught equal to CH. So the equation will change into Q initial minus CH. Then from Q initial, we will rearrange the equation and we will get Q initial equal to A dH over dt plus CH. So this equation represents the differential equation for head. Now we will enter the Laplace transform part. From the differential equation earlier, we will Laplace transform on both sides, but it is a little different because to find the transfer function, we need to multiply by s in the Laplace domain. So we will get Q initial equal to AS bracket SHS minus H0 bracket plus CSHS. Then from the Laplace transform, we will get the answer. For the answer in 1, we will look at the table and then we will get the answer HS over Q initial S equal to 1 over SAS plus CS. However, since the equation state that Q naught is equal to CH, from the Laplace transform, we will get the answer HS equal to Q naught S over CS. And then from the equation we get earlier in the equation 1, we will get Q naught S over CS Q initial S equal to 1 over SAS plus CS. Then the final answer will be Q naught S over Q initial S equal to 1 over 1 plus AS over CS multiplied by S. Then from all this, lastly we will get the time constant for the transfer function is torque equal to AS over CS. So as the conclusion for this question, Laplace transform is used to solve the differential equation we get earlier because it can simplify the very complex problem at first to the easier problem for transfer function that we get in the end. So it goes without saying that Laplace transform has a tremendous role in engineering field. Thank you.
Hi, my name is Sana Sofia Bitasabi. So my metric number is AN230047. So the topic for my maths project is application of first order differential equation is the following body. So there is 3 objectives, which is develop a mathematical model, understand the velocity profile, and derive the analytical solution. So for the next slide, as you can see, there is a situation for the problems, and then the problem equation is the differential for the velocity vt of the following sky level is dv t over dt equals g minus k over m vt. So the given initial value, as you can see, g we have a 90.8, and then for the k air resistance coefficient 0.25, and then we have the mass of the sky level 75 kg, and then the v naught, which is 0 meter per second. So t over dt equals to g minus k over m vt. And then as we can see, for the general equation, first we rewrite the equation, so it becomes to dv t over dt plus k over m vt equals g, and then we integrate the factor, so it becomes to the integrating factor of mu is given by mu t equals e integrate k over m dt equals e integrate k over m t. So and then we multiply through by the integration factor, as you can see, and then the fourth for the solution, we integrate the both sides, so we have the vt exponent k over mt equal gm over k exponent k over mt plus c. And then for the fifth solution, we have to solve for vt, and then for the sixth, we apply the initial condition, which is v naught is 0. So we have the final for that, c equals to v naught minus gm over k, and then we substitute back to the c for the into the solution, which is vt equals mg over k plus v naught minus mg over k exponent negative k over mt. And then the final for our equation, so we substitute the given values on the first slide we've seen, and then for the final answer we get is vt equal 2940 bracket 1 minus exponent negative 0.00333t close bracket. So that is our final answer. So for the last slide is the conclusion, which is the velocity of the skydiver falling for an aeroplane under the influence of the gravity and air resistance can be modeled by the differential equation, which is dvt over dt equals g minus k over m dt. Using the integrating factors and solving the first order linear differential equation, we derive the general solution vt equal mg over k plus v naught minus mg over k close bracket exponent negative k over mt. The solution reveals that the skydiver velocity increases over the time from the initial velocity and subsequently approaches a constant terminal velocity gm over k as the time progresses. This terminal velocity represents the balance between the gravitational forces pulling the skydiver down and the air resistance opposing the motion. That's all from me. Thank you.